But one of the things you want to do when you're going through the unknown analysis is you want to think about the reactions that are happening. Probably the easiest way to map something like that out is to look at the flow chart, because the flow chart tells you what products to expect at that. But we can go a step beyond that, and this is something you want to think about as well. And that is, when we look at the flow chart, we have something like the unknown here, and then in the first step we'll add some HCl. And when we add the HCl, we could get a precipitate of AgCl, solid, etc. We just have the steps in the flow chart. And what we're going to do is we're going to look at these steps based on the chemical reactions that happen there. And so for the silver ion test, we have a set of observations, and these observations are associated with some kind of equation that we can come up with. So the first observation is, if we take our unknown aqueous and add HCl to that, we should get a white PBT if silver is present. And the product is silver chloride, so the equation we can figure out here, it's going to be silver ions in our unknown reacting with chloride ions in the HCl, gives us a precipitate AgCl. Okay, then what do? Well, we decant, we separate, we wash, and then we take that precipitate and do what? And so the observation here would be the precipitate from step 1 is allowed to react with well, and this, what was it? Was it ammonia?
It's nitric acid.
Nitric acid at this point? See, this is why, because somebody came up to me and asked me, well, they made a mistake here at this particular step, but, some of these you could figure out, how severe of a mistake it was if you know the chemical reactions that are happening. Maybe you could potentially reverse it, So, for example, as far as mistakes go, if you add nitric acid here instead of the ammonia, would you just toss it and start over, or is that a recoverable mistake? Yeah, it's recoverable. So we could add some excess ammonia here, and what happens is the precipitate ends up dissolving, and we end up with a CCS. CCS stands for clear colorless solution. And so the equation here is just going to be this: we got silver chloride, and then we need at least 2 ammonia to react with this to form the diamine silver ion plus chloride. That would be our CCS, it would just be all aqueous. Okay, the next step of the procedure, we take our CCS from step 2 and then add nitric acid here. We add the nitric acid, then we end up with a white PBT again. And so the reaction, or the equation for this particular observation, can be written in different ways. In chapter 18 we'll write it totally different, but for this, what we'll do is we'll just look at this equilibrium that we have here. Oops. Oh, this is right. And what does nitric acid attack in that equation? If it's an equilibrium, what would it attack? It would attack the ammonia, the strongest base present. So if it attacks the ammonia, we end up forming ammonium. And so what we'll do is we'll decrease the concentration of ammonia. As that happens, this equilibrium shifts left, and we reprecipitate out silver chloride. we can completely kill off the ammonia and then completely precipitate out by adding, just continually adding H+. So this is a shot of the H shift to the left. All right, after we've gone through all these steps, then we say we have a positive for silver ion. Positive test for silver. When we're doing these, we got to think. Let's say steps 1 and 2 work, but step 3 didn't. Is that a negative for silver? Maybe, maybe not. You have to think about what else would give you a precipitate with chloride. But normally a negative test, let's say nothing precipitated here and you got nothing else here, then we have a negative test for silver. But a negative test, the way we interpret that is, does a negative test mean we definitely do not have silver ion? No. A negative test, all of that says is that it wasn't detected. It wasn't detected because you might not have it. It wasn't detected because it might be a really low concentration. So if it's a really low concentration, it's below what's called the detection limit of the test. A lot of tests, they have different sensitivities. Some tests are highly sensitive. For example, iron. The iron test that you guys are doing in this lab is highly sensitive. And so I see people using those rusty old tongs, worrying. When I see them using it, I'm worrying that a piece of iron is going to drop in there and rust, give them a positive test. And so other tests are less sensitive. Like, for example, the calcium test. That's a tough one, right? That one isn't nearly as sensitive as some of the others. But there are clues that drive you along because, these previous observations and equations, what interfering species can lead to these kinds of observations. You can think through it because you kind of have an idea of what the possible ions are that are present. All right, so that's silver, and then we go on to iron. Was it iron 2 or iron 3? Okay. Iron 3 plus. The iron 3 test. And we do it separately. Even though we're doing all the ions together, when we think about it, we're just looking at the chemical properties. What are the chemical properties of silver and some of its compounds? Over here, what are the chemical properties of iron 3 and some of its compounds? And so we're just getting an idea of how these things behave. So in the first step here, we took our unknown. Let's say our unknown contains iron, and we add HCl. Did HCl react with the unknown containing iron? No, if we have iron only, there should be no reaction here with iron. And the equation for this is observation. Let's write the equation. Iron 3 plus HCl, there's no driving force for any kind of reaction for that. And so we get NR. And so this is important because iron 3 won't react, but the silver ion will react. That's important for separation here. And so even though it's a no reaction, some people say, isn't the no reaction not a chemical property? I mean, if it doesn't react, then is it a chemical property or is it not? And what I say is it is a chemical property. You need to know that iron 3 won't react with HCl. That's important in understanding the chemistry of iron 3. All right, so then we take this solution, from 1 that still contains iron 3, and then we add to that? We add base, like for example, do we add sodium hydroxide? Because what do we want? If you look at the flow chart, we want to take that iron 3 and make it iron 3 hydroxide. And so the simplest way of precipitating out a hydroxide is by adding sodium hydroxide. But are we adding sodium hydroxide? No. We aren't adding sodium hydroxide here. Instead, we're adding ammonia and ammonium. Why are we adding ammonia and ammonium? Does ammonium sound familiar? Ammonium? We haven't gotten that far. Ammonium is a buffer. It's a conjugate buffer, the Henderson-Hasselbalch buffer. You know, you have your base, acid, conjugate pair. And so why are we adding that?
That's a way of neutralizing?
It's not a way of, we're trying to do a precipitation here. And the precipitate, how do I know we're trying to do a precipitation? I see it in the flow chart. I'm going from an aqueous solution to iron 3 hydroxide to precipitate. And so why am I trying to precipitate out with ammonia and ammonium? Uh-huh.
Because it'll precipitate out the iron 3 ion concentration.
Well, we want it to precipitate out the iron 3. Yeah. And so, but we could have added sodium hydroxide and precipitate out the iron 3 as well.
But is it like the concentration of those two, like the hydroxide ion?
Yeah. This is a way of controlling hydroxide because, you know, we should precipitate out all insoluble hydroxides. Right. Like magnesium hydroxide. Is magnesium hydroxide soluble or insoluble? It's insoluble. So we should precipitate out magnesium hydroxide, iron 3 hydroxide, aluminum hydroxide, right? But we don't precipitate all insoluble hydroxide. And so the reason why we're precipitating out with this buffer solution is to control the pH. If the pH gets too high, we precipitate out all the cations that will precipitate out as insoluble hydroxides. And so what we're trying to do is we're trying to only precipitate out the plus 3 cations. The plus 3 cations are more aggressive than the plus 2 or less aggressive than the plus 2? Plus 3, more aggressive or less aggressive towards hydroxide? It's more aggressive. Plus 3 has a higher positive charge, hydroxide is negative. And so what we do is we control the amount of hydroxide by buffering the solution. We need to make sure that the pH of the solution is above 7 so that there's plenty of hydroxide, but below about 9. Because if we hit pH 9 and higher, we're going to start precipitating out everything. And so what this is called it's called a selective precipitation. We're just trying to precipitate out the 3+ cations and leave the 2+ and the 1+ cations in solution. Okay, and then we get a precipitate. With iron 3, do you know what the color of iron 3 hydroxide is? It's kind of a brown precipitate. And so the reaction for this is the ammonium is there, you know, ammonia is a Kb, it's a base. Ammonium is an acid. And so what's generating the hydroxide for precipitation? It's ammonia. And since ammonia is generating the hydroxide for precipitation, the equation for this observation is that the iron 3 plus 3 ammonia plus 3 H2O liquids gives us iron 3 hydroxide solid plus 3 ammoniums. We don't want to add too much ammoniums because if the solution gets too acidic, what's that going to do? Well, too much ammoniums will push this equilibrium to the left and dissolve or precipitate. And so we just have to have the right balance, you know. And that is, we just have to make sure it's basic but not too basic. We definitely do not want to precipitate out things like magnesium hydroxide, white PPT. All right, so this is the reason that we use ammonium to control the balance in this. Now, having ammonium hurts us because the more product we have here, the more impacted this is by the common ion effect. If we have a lot of ammonium here, are we going to get as much precipitate forming? No. But the thing is you need some ammonium there, otherwise you're going to get some of the other ions precipitating. And so maybe it's not the cleanest separation, or maybe it is clean. It depends. Chapter 18 will look at this. All right, after we do this, then what?
But aren't we actually using sodium hydroxide for that?
The next step. Yeah, this is weird because now what we're doing is we're taking the precipitate from 2 and adding sodium hydroxide. Excess sodium hydroxide. So what's the difference between adding sodium hydroxide here versus here?
There's no iron.
Yeah, basically here you've washed out all the other ions. There are no other ions. And so here what you do is you separate out the precipitate from the other ions in solution. So when we add the sodium hydroxide, there's no magnesium ion to precipitate with it or any other ions to precipitate it with it, right? But that still leads us to the question, why are we adding sodium hydroxide? Didn't we already precipitate out the hydroxide successfully? What is the purpose of the sodium hydroxide? Is the purpose of the sodium hydroxide to react with the iron? Or is it to react with something else? So you could look at the flow chart and tell me, what does it react with? What is the sodium hydroxide supposed to react with? Not with hydrogen peroxide. Did anything happen to iron 3 hydroxide? Did it stay as iron 3 hydroxide? Actually, nothing happens. If you look, and you should put the flow chart into your lab notebook. You can photocopy it and tape it in there if you want. But actually, this one we get NR for the iron. You know, when we add excess hydroxide to iron 3 hydroxide, nothing should happen. So why are we adding it? Because if I look, here's my observation. My equation is going to look like this. Equation just will be iron 3 hydroxide solid plus hydroxide excess yields NR. No reaction. And so what was the purpose of adding the hydroxide? The purpose of adding the hydroxide was not to react with the iron. It was to react with something else. Aluminum, right. The purpose of this excess hydroxide was to react with aluminum, and what happens is aluminum hydroxide precipitate, AlOH3, disappears and is replaced by, what's that? The name of that complex? AlOH4 minus. What's the name of that? Tetrahydroxo aluminum or aluminate? Aluminate. Tetrahydroxoaluminate ion. And so the reason for the excess hydroxide was not to react with the iron, but it was to react with aluminum. The aluminum hydroxide precipitate actually reacts with the excess sodium hydroxide. What kind of reaction is that? It's not a signal replacement. It's not a redox. It's a Lewis acid-base reaction, right? We're forming a complex. It's a Lewis acid-base reaction. And so what is the Lewis base? The hydroxide. Is hydroxide a good Lewis base? Yeah, I would think so. You know, it's a pretty good base. It's a strong base, right? We typically think of hydroxide as being a strong base. And so why, you know, if hydroxide is a good Lewis base, why does it attack the aluminum and not the iron? Because if I think about it, iron hydroxide, iron 3 hydroxide is just iron 3 ions. Aluminum hydroxide is aluminum plus 3 ions. The same thing, plus 3 iron, plus 3 aluminum. What's the difference? Why doesn't hydroxide attack my iron just like it attacked aluminum?
Charge density.
The charge density of iron 3 and aluminum 3 is very high. So both of them have quite high charge density. You know? They're very small ions, both of them. Uh-huh.
Is it because aluminum hydroxide dissolves from the sodium hydroxide and iron?
That's factual observation. The aluminum hydroxide dissolves, but the iron hydroxide does not dissolve. And so the question is, why? The reason I'm asking this is because this is like saying, if I had sodium hydroxide, I could neutralize HCl, but it wouldn't neutralize nitric acid. Does that make sense? Would it make sense? You know, if you have sodium hydroxide, it'll neutralize any Bronsted acid, right? Now we have hydroxide, sodium hydroxide, acting as a Lewis base. Why doesn't it react with any Lewis acid? Right? In other words, if you don't like to memorize stuff, then tell me how you would have predicted this. Tell me how you would have predicted that hydroxide would react with aluminum but not with iron. Hydroxide precipitate. How would you have predicted that? You know, I can make easy predictions because I'll tell you, sodium hydroxide will neutralize HCl, it will neutralize acetic acid, it will neutralize nitric acid, it will neutralize any of the acids that we're familiar with, right? It's totally indiscriminate. But why is hydroxide so selective in what it reacts with? It likes aluminum but doesn't like iron? Why?
Iron's already bonded. It's already hydroxide.
Well, aluminum was already bonded to hydroxide. The reaction I'm talking about is this: aluminum hydroxide, solid, plus excess hydroxide. We get a reaction here, which forms the tetrahydroxyaluminate. So why will it react here but won't react here is the question. This is a Lewis acid, this is a Lewis acid, this is a Lewis base, this is a Lewis base. Lewis acid, Lewis base, they should react, right? They should react, right?
Does that have something to do with the orbitals?
It does, yeah. And so what it boils down to is not just a simple charge density. If it were just simply charge density, then they should react. You know? Bronsted acids and bases are simply charge density because the acid is each, the higher the positive charge on the acid, the better the acid is. But here, you know, we got equal charge. Maybe the density is going to be a little different because the size is a little different, but not hugely different. And so it has to do with,
Is it, this is just a random guess, is it because of like the size and like the dipole attraction?
that's usually what we look at. And based on the size and the dipole attractions, this kind of stuff, you would expect it to react too. It should react. Why isn't it reacting? And so that means that Lewis acid-base reactions are more complicated than Bronsted, right? Because, you know, would you have been able to predict this? Reaction, no reaction. Could you have predicted that? No. And so what we need is we need more, better theoretical understanding of what's happening here. And better theoretical, you know, understanding is we're forming coordinate covalent bonds here. What's the theoretical understanding of coordinate covalent bonds? What's the theory behind bonding?
Valence bond theory?
Well, valence bond theory fails, unfortunately, for complexes. We don't use valence bond theory for complexes. We use MO theory. And so to answer this kind of question is more complicated. So this is why we need like factual data, because it's easier sometimes. You know, memorizing little facts here and there is easier than trying to understand the theory in detail, because the theory is quite complicated. Well, although people have tried to make the theory easier, a lot easier, by introducing HSAB. HSAB is this is kind of a simplification of quantum, so you don't have to dig into all the mathematics. You can just do it by simple rules of reaction, right? And so this is why I talked about HSAB, because, you know, in order to properly predict this, we need quantum mechanics, or the simplification, which is the HSAB, to really get a handle on how to predict these things. But for right now, we're just in observation of, you know, facts, basically. All right, I don't want to talk for too long, so I'm going to just finish up iron and then we'll start. What's the next step here? So it doesn't react with excess hydroxide. Then what do you do? You add some hydrogen peroxide. So tell me, does iron 3 hydroxide react with hydrogen peroxide? You know, when you normally think about hydrogen peroxide, what chemical property comes to mind? Yeah, gas formation, decomposes, right? The decomposition is a redox, but normally hydrogen peroxide is thought of as an oxidizer or reducer in redox. It's an oxidizer, pretty good oxidizer. And so one of the chemical properties of hydrogen peroxide is it's an oxidizer. H2O2. The hydrogen peroxide is not there to react with the iron. The hydrogen peroxide is there to react with what? What becomes oxidized by the oxidizer hydrogen peroxide? Chromium. The hydrogen peroxide is there to convert chromium from +3 to plus. Or it's there to convert chromium 3 into dichromate or chromate. Do you guys see it? It's all on the flow chart. It should be all there. Does it convert chromium 3 to dichromate? It converts it to dichromate. Dichromate has chromium in what oxidation state? What's the oxidation state of chromium in dichromate? No, not 4. It's 6, yeah. +6 is the oxidation state of chromium in dichromate. And so we're using hydrogen peroxide to convert chromium from +3 to +6 in dichromate. But what do we do about iron? Should we convert iron 3 into iron 6? +6? Iron +8? Iron +4? Do any of those charges sound? No. And so here, with hydrogen peroxide, we expect no reaction. So this is the equation, sorry. The observation is the brown precipitate from 3 is mixed with hydrogen peroxide, we get NR. Reaction. It's not going to oxidize iron. It's already maxed out in terms of oxidation state. Iron 4 is not happening. Okay, what's the next step? The next step is we heat it to kill off the hydrogen peroxide, which you can either show or not show, you know. The heating step to kill off the hydrogen peroxide, what does hydrogen peroxide decompose into? Water and O2 gas. So you heat it to bubble off the oxygen, decompose it. And then what do you do next? with the precipitate. And so we'll take the precipitate from step 4 and add
HCl acid.
HCl. If we add HCl, then what happens to the precipitate? It dissolves, and we should end up with something like a clear yellow solution, perhaps. The color might be difficult to see, but the equation here is iron 3 hydroxide, solid, plus 3 HCl's yields iron 3 chloride, which is aqueous, plus 3 waters. And the iron 3 chloride should have a slight yellow color to it. All right, then following this along, what do we do to the solution 5 here? Potassium, hexa, you know, remember hexacyano?
Ferrate.
Okay, ferrate,
Ferrate 3.
close,
Very
ferrate 2. Potassium hexacyanoferrate 2. And then, what did you get? A blue precipitate. You have to be careful because you'll probably end up with a blue solution as well. It's not the blue solution that's positive, it's a blue precipitate. And what is the precipitate? Well, iron 3 chloride, we have to remember that that is a strong electrolyte, right? Soluble salt. And so we have our iron 3 ions reacting with, is this a strong electrolyte? Is that a strong electrolyte? Yes. How come? Potassium salts are soluble. Soluble salts are strong electrolytes. And so what we have here is we have the hexacyanoferrate ion. And then we just got to get the ratios right. That is, for every, we need 4 irons and 3 hexacyanoferrate 2s. And then we're going to get Fe4, FeCN6, 3. And this is the precipitate. Precipitate's a very famous precipitate, Prussian blue. I think they use it in blue jeans. Right? Although, why would they put cyanide in blue jeans? Would you? You wouldn't want to wear something with cyanide on it, would you? Well, those cyanides are not really free ions. Those cyanides are actually covalently bonded to the iron, and so they're pretty well stuck on there. They aren't going to come off, rub off, and start to poison you slowly, I think. So I think you're all right. All right. So this is kind of what you think about when you're going through. You're thinking about, you know, the observations for the particular steps and the equations for the particular ion. You know. And that will give you a clearer picture of what's going on, because oftentimes what happens is something doesn't happen, or colors don't match. You know, colors you have to be careful, because colors depend on what other contaminants are in the mixture, and so the colors can vary dramatically. In geology, you know what the geologists do is they have a scratch test. Have you ever heard of that? The scratch test is to determine color. And the reason is because crystal size, how big your crystals are, changes the color. And so, for example, silver metal, what color is silver metal? Silver metal is silver in color, right? Unless the crystals are tiny. If the crystals are tiny, then it doesn't look silver anymore. Do you know what color it looks? Black. Yeah. So silver can be black when it's finely divided. And so the scratch test is to convert whatever you're looking at into a powder with consistent crystal size so that you can cross-compare it for color comparisons. And so always beware of color, because I know a lot of people get hung up and they're looking for exactly the same color that they might have seen before, which you might not get. It doesn't mean you don't have it. It might mean you don't have it, but you could have it, it's just discolored. Or you have more, you have less. Or the crystals are a little different in size. That's it. All right, any questions? All right, again, just to reiterate the rules, no talking about the tests amongst each other. Okay, no comparing your precipitates or solutions. Okay, thanks.